Google has just released a recurrent Gemma family of models, which contains models of 2 billion size and 9 billion size, both in base and instruction tuned variants. In this video, we will be installing a recurrent Gemma locally on our system, and then we will test it out on various benchmarks. Before I do that, I will also be describing one unique feature of these models, which is their new architecture called as Griffin architecture. I also want to give a huge shout out to our friends at Massed Compute for sponsoring the VM and the GPU being used for this video. If you are looking to rent a GPU on affordable prices, I will drop the link to their website in video's description. Plus, I am also going to put a coupon code which is going to give you 50% discount on an already discounted offering. Okay, so first let's check what exactly this Griffin architecture is. As I mentioned, Recurrent Gemma is a family of open language models built on novel recurrent architecture developed at Google. Both pre-trained and instruction-tuned versions are available in English. Like Gemma, which we have covered a lot on the channel, recurrent Gemma models are well suited for a variety of text generation tasks, including question answering, summarization, and reasoning. Because of the novel architecture, which is Griffin, recurrent Gemma requires less memory than Gemma and achieves faster inference when generating long sequence. It takes text as an input and then output is in English generated language text in response to that input. It could be an answer to the question or a summary of a document. Now, this Griffin architecture is a neural network design that uses a combination of linear recurrences and local attention to model sequence. It avoids global attention, instead it relies on local attention and recurrences. It also compresses input sequences into a fixed size state, reducing memory usage and enabling efficient inference on long sequences. It's a key component of the recurrent Gemma 2 billion model, which achieves competitive performance with transformer based models like Gemma 2 billion while offering improved efficiency. So that is what the recurrent Gemma is, and that is what a Griffin is. Now let's go to my local VM and then we will get cracking on the installation of this model. This is my Ubuntu system where I am running Ubuntu 22.04, and this is my GPU card of 48 GB of VRAM. Let me clear the screen. Also make sure that you have Conda installed to keep everything separate from your local installation. I already have it. Let me create the Conda environment, which I'm just calling Gemma. Do not take too long, and then we will be stepping into that environment, and you can see that in the parentheses on the left. Now first install few of the prerequisites like torch and then transformers. Let's wait for it to finish. This takes around 30-40 seconds, and that is done. Let's also install the transformers from source because it's a very new model. We need it from the source, and I'm also installing accelerate just in case to speed up the things. Let's wait for it to finish, and that is done. Let me clear the screen, launch my Python interpreter, and you can run these commands in a Python py file instead of interpreter if you like, but I just want to show you the demo how it works step by step. So that is why we are importing the stuff, and then let's specify our brand new recurrent Gemma 2 billion model. This is the model ID. Let's also set the D type to bfloat16, and then let's grab our auto tokenizer with the same model ID, and that is done. Next up, we need to download our model, which of course is our recurrent Gemma 2 billion model, and it has started downloading it. There are two tensors, and each tensor is, it seems the first one is 4.97 gig. I think the second one is also similar, so let's wait for it to finish downloading, and model is downloaded. Now let's define the ChatML prompt template, and you can see we are just defining the roles here. There is a user who asks the question, and then the content of it is like this. Let's specify our prompt too, and I'm just going to apply the chat template on that prompt and see if that is able to generate it. Let me actually quickly show you this prompt because there is an interesting information I wanted to share with you. There you go. So you see in this one there is a beginning of sentence where it has something like state of turn and then user, and then this is state of turn and this is end of turn. So as you can see, each turn is preceded by the start of turn. So like this one or this one is preceded by start of turn. So what happens here is that this start of turn, there is this start of turn delimiter, and then the role of entity, and the role of entity could be user for content supplied by the user or model for LLM responses. Turn finish with end of turn. And you can follow this prompt format to build the prompt manually if you need to do it without the tokenizer chat template. So instead of using this one, you can simply build your prompt like this. And if you use this format, the responses will be very optimal from the model. If you don't use this, still the model will supply you the response, but it will not be as good as it should be. Okay, so let's convert the question which we have asked. The question which we asked was write 10 sentences ending with the word beauty. So let's see if the model is able to generate it. Most of the models fail by the way in this one. Now let's ask the model to generate the output, and I'm just restricting it to 150 words. And let's ask the tokenizer to decode the models one. There you go. Maybe I will increase this because it has just curtailed it. But anyway, you can see that this is fail, this fail. So most of them have failed. It hasn't really, out of it was not able to generate even a single sentence which ends in beauty. Anyway, let me clear the screen and let's ask a couple more questions. So I'm clearing the screen, and now let's ask it, tell me a funny joke from Greek mythology here. Let's print it out. So here it says, okay, it's the end of sentence. What do you call a Greek god who is always late? A TARDIS. Okay, cool. Let's ask it one more question. In this one, I am asking it, which of these objects is not like the others? Apple, banana, potato, chair. It says the chair is the object that is not like the others. The apple and all of these are fruit, while here is a piece of furniture. Very good. And now let's ask it a reasoning question. Now, in this reasoning question, I'm just asking it that John, a man with extensive criminal history that includes theft and all that stuff, he finds a wallet full of money somewhere. So I'm asking the model that given his previous criminal history, is John going to keep the wallet or cash, or would he return it to the rightful owner? So now you see that it says that start of the turn, John attempts to return the money to his rightful owner or not. Rationale, moral obligation, legal consequences, community reputation, personal satisfaction, and then it is making the prediction. It is more likely that John will attempt to return the money to its rightful owner than pocket it for himself. The moral obligation and all that stuff. So it's a very good answer. Normally the model, all the models, most of the models say that John is going to keep the money given his previous history, but here this Gemma model has gone against it, and it has also given us a rationale behind it. Amazing. Now let's check out its math capabilities. I'm clearing the screen, and now here the math equation is this. The correct answer is 20. So let's see if model is able to do that. Nope. Okay, that is okay. Now let's ask it a couple of coding questions. In this coding question, I'm asking it, show me a Python script that draws a Mandelbrot set. Let's print it. Amazing, very nice, looks really good. You see start of turn, then it is importing the libraries, setting the parameter for the model plot. It's a very complex geometrical concept, so I believe it has done wonderfully well by also plotting it. Great stuff. And then it is also giving the explanation towards the end, point by point. Very nice. Let me clear the screen and let's ask it to translate the code in another one. So you see that here I'm asking it translate this C code snippet into Ruby, and then I have just given it a very simple small C code, and there you go. It has produced the code, which looks really good. So all in all, I believe real good model. Math progress seems a bit low, but other than that, reasoning, language generation, and also the coding looks quite good. So that's it, guys. Let me know what do you think about it. There is also a 9 billion model, but I just wanted to show you the full model, so that is why I selected 2 billion. The architecture of 9 billion is also the same, albeit there will be more parameter, it might be more performant. Let me know what do you think. If you like the content, please consider subscribing to the channel. And if you're already subscribed, then please share it among your network, as it helps a lot. Thanks for watching.